And it's without transferring matter. We're not taking this and we're not transferring this spring from here over to here, right? We're just transferring energy within this realm, okay? So particles within the medium oscillate or vibrate back and forth with simple harmonic motion, but don't actually move in the direction of the wave itself. This is kind of hard to understand. But some examples of this are sound waves. What's something else that would be like a sound wave? Where we have something that transfers energy from one location to another without. Keep thinking in terms of waves. Nope, think in nature. Waves, ocean waves. You can see them building and coming into the shore, and then the water goes back out and it takes that energy with it. What's another one? This one we might not see, we're not used to them here. All right. Earthquakes, okay? They radiate energy out, but you don't actually physically move the land. It's just the energy that radiates out creates the wave, and it breaks the soil and the earth apart, but we don't actually move that dirt or that soil, okay? So it can also be transferred by matter when two or more objects collide. So what would be two things where we would transfer energy where two objects collide? Okay. Let's think more real life. I mean, particle accelerator is real life, but you'd have to be a research scientist to be there. Two things collide. Right? Two pool balls knocking together. That's where we have energy being transferred by the matter. Another one. We have a transfer of energy when two vehicles collide. Okay. Now there are very specific things that we look at when we're looking at waves. So I'm just going to draw the line here, and as we go through it, we're going to talk about it. Okay. Wave propagation is the direction of the wave movement as it travels through a medium, and a medium simply means a material or a substance. So air is a medium, water is a medium, the glass pane of a window is a medium. Okay? So if we were to say, we've always been calling it DOM, direction of motion, now it's wave propagation. Okay? Frequency, the number of complete wavelengths that pass a certain point in 1 second. Darn smartboard. Okay, I'll show you that in a second. Period is the time it takes the wave to travel one complete wavelength. And so in order to answer those two pieces, we need to know what a wavelength is. And a wavelength is the distance between two neighboring crests or troughs. So up here we have crests. And down here we have troughs. Okay? And so one wavelength would be from crest to crest. This is one. And the symbol for wavelength is this funky little symbol. I don't tend to draw it with the little hook at the top. I just draw like an upside down inverted Y. Okay, there you go. Or you could have a wavelength from trough to trough. This would be one wavelength. Okay, either or, but it has to be crest to crest or trough to trough. And an amplitude, whether it's a minimum or a maximum displacement for equilibrium, and it goes from the equilibrium line, that's what this is here. This line here is the equilibrium line. And so from here, from this point here to this point here is amplitude. From the line of equilibrium to a crest or the line of equilibrium to a trough. This is amplitude. Okay? So now it says, let's go back into frequency. Frequency is the number of complete wavelengths that can pass a certain point in 1 second. So if I was to like make a little window and we put time markers on here, this would be starting 1, 2, 3 seconds. And we had this. That's the wave pattern that we had. It says the number of complete wavelengths, which is a crest to a crest or a trough to a trough, in 1 second. So here's our time marker right here for 1 second. And we see that we have one crest to one crest, and we have one crest to another crest right at this point. Sorry, I have fruit fly. So we would have two wavelengths in that 1 second. Two complete wavelengths in that 1 second. Okay? And it says here for period, the time it takes to complete one wavelength. So we would need to time from crest to crest. That would be period. This here, being two wavelengths, is our frequency. Okay? So there's two types of mechanical waves. There's transverse waves. And so mechanical waves where the particles of matter vibrate or oscillate perpendicular to the direction of travel. So if this is our direction of travel, and we see that the waves are going like this, up and down. Okay? So it's perpendicular. So if take my slinky and my direction of travel is this way, if I flick my wrist and I get this up and down, I can't get multiple, maybe I can. Okay, the waves are going up and down like this, but they're traveling this way, right? I start my flick this way. If I could, let's just try it. I flicked my wrist. And the wave traveled to the left. It traveled from me towards Princess, but we sent the wave going up and down like this. Okay? So this is what we call the particle vibration. When I flicked my wrist and the wave went up and down, and we see here that we have 90 degrees to each other. Okay? Now, we have what? We also have longitudinal waves, and where they travel parallel to each other. So if the direction of motion or wave propagation is to the right, and I send my waves this way, what it looks like is it looks like a series of lines. And these gaps in between show you that up here we have this motion that we can physically see. This shows us that we have travel. So this is like a wave, a wave, a wave. And we have wave motion. And we have particle motion. Okay, and so this is parallel. I'll show you what that looks like, the slinky. We're going to look at some words that we learned before. We might not remember them. The law of reflection. Okay, this is our reflecting surface when we put lines like this. Okay, reflection occurs when a wave collides with a barrier and then it bounces off that barrier and comes back. And the law of reflection says that the angle of incident is equal to the angle of reflection about the normal line. So this one here, the normal line, is always perpendicular to the reflecting surface. And so here we have an angle come in, an incident ray come in. And according to the law of reflection, it will go back out at the same angle that it came in to the line of normal, not to the reflecting surface, to this imaginary line that makes 90 degrees. And so we go back out. And we call this the reflected ray. Okay, so the angle of incidence is equal to the angle of reflection. In an ideal medium, amplitude and wavelength remain unchanged. So if it came in with a certain amplitude, in theory, it's going to go back out at a certain amplitude. Okay? So first example, one end of a spring is attached and fixed in place to a wall. This is the wall. It's attached and fixed there. Draw in the reflected wave that would result when the incident wave travels through the spring. So here's the spring, and we flicked our wrist, and here's the incident wave. It's coming into the wall like this. what would we see happen in the spring coming back? If it comes in as a crest, it's going to go out as a trough. And this is the reflected. Okay? A ray of light is reflected in series from two mirrors, A and B. I got to draw you a diagram. So this is mirror A, this is mirror B. It comes in like this. This is 98 degrees. And it comes out like this. And it goes out like this. And it tells you that this is 50 degrees. And this is normal to A. All right, I think that's everything that's given to you. Yep. Okay, so this is a ray of light is reflected in series from two mirrors A and B as shown in the diagram. What is the angle of reflection from mirror B? So what we need to do is, perpendicular to mirror B, we need to draw in this line of normal. And this would be our normal to B. And the question is asking us, what is the angle of reflection? The angle of reflection is always to the line of normal. So it's asking us for this angle. That's what we're looking for. Okay? Now, this angle here, the line of normal always makes 90 degrees to the surface. Always. So this whole angle here is 90 degrees. Because it's the line of incidence is equal to the line of reflection about the normal, we know that this angle here then is going to be 50 degrees, which means that this inside angle is actually going to be 90 degrees minus the outside 50 degrees for a total of 40 degrees. This angle here is then going to be 180 degrees. A triangle makes 180 degrees. Minus the 98 that it tells us, minus the 40 degrees that we just figured out, and we're left with 42 degrees. So this angle here is 42 degrees. Now, we need to remember the line of normal always makes 90 degrees to the surface. So this whole angle here is 90 degrees. Take out that 42 degrees and we are left with 48 degrees for this angle here. This one here. So that is the new angle of incidence. The angle of incidence is always equal to the angle of reflection about the line of normal, which means that the theta that we're looking for, the angle that's reflected, is going to be equal to 48 degrees. Okay, so the speed, that's what this word is. I'll write it in there. The speed of a wave as it travels through a medium depends on the medium itself. Okay? If the medium remains constant, the speed of the mechanical wave will remain constant, which means that you could use V equals D over T. But if the medium changes, if it goes from air through glass, which is how we see the vehicles outside in the parking lot, it's going from air through glass back into air, the speed of the wave will change. And so, sound waves travel faster in liquids than in gases, travels faster still in solids. The speed of water waves depend on how deep the water is. The speed of a wave in a rope depends on the weight and the thickness of the rope. The speed of a wave through a slinky, right? Oh, I left it on the table. The speed of a slinky. If I have my slinky only expanded this much and all of this is drooping, it's going to be different than if I fully extend it and flick it. I'm not going to get as big of a wave, and it's not going to travel at the same rate. So we can figure all of that out. We look at velocity is equal to wavelength times frequency. And I will not say wavelength. This symbol here, this symbol right here, this is called lambda. That's what this symbol is called. I need a B first. It's called lambda. And I will say V is equal to F lambda. When I say lambda, I mean wavelength. When I say wavelength, I mean lambda. I just call it by the symbol. Okay? So V is equal to F lambda, V being the speed of the wave, lambda being the wavelength, so from crest to crest or trough to trough, and frequency is always measured in hertz. If it gives you megahertz, change it to hertz. If it gives you microhertz, I've never seen that, but change it to hertz. Okay? And this is called the universal wave equation. We use this concept right through to the end of Physics 30. Okay. A wave has a speed of 0.50 meters per second and a wavelength of 2 meters. What is its period? So it has a speed of 0.50 meters per second and a wavelength of 2.0 meters. And it's asking us to figure out period. Period, right now, is calculated by 1 over F. In order to solve for F, V is equal to F lambda. Okay? So F is equal to V over lambda, which is 0.50 meters per second divided by 2.0 meters. And you can see from unit analysis how seconds, up here it says hertz or s to the power of -1 or 1 over s. You can see how that happens. And then F would be equal to F. You went one step too far. 0.25 hertz. Now we can solve for period. 1 over 0.25 hertz is equal to, Daniel, 4. And period is measured in what unit? Seconds. Okay? All right. An earthquake can produce two types of waves, a P wave and an S wave. An earthquake occurs 52 kilometers away from a city if the P wave travels at 7 kilometers per second and the S wave travels at 5. Calculate how much sooner the P waves reach the city before the S waves. So, this is not changing the medium, right? It's the ground is the ground. And so, first let's write down our information. The distance to the city is 52.0 kilometers. The velocity of the P wave is 7.0 kilometers per second, and the velocity of the S wave is 5.0 kilometers per second. And it's asking us to find out how much sooner the P waves reach the city before the S waves, which is the change in time. The medium is not changing. Which means that we can use the velocity is equal to distance over time formula. And then the other thing to note is that because this is in kilometers, and these are kilometers per second and kilometers per second, we're okay to not convert units. Time is going to be equal to distance over velocity when we rearrange the formula. So time of the P wave is going to be 52.0 kilometers divided by 7.0 kilometers per second. And the time for the S wave is going to be 52 kilometers divided by 5.0 kilometers per second. And we get what two values? Then the S wave. Okay? While floating on a tube on a lake, you note that you bob up and down 40 times in 5 minutes, and you estimate that the distance between the crests is 4 meters. What is the estimated speed of the water? Yep. So, the wave length, it says the distance between the crests, which is one full wavelength, is 4.0 meters. It's asking us to find the velocity, and it says that the frequency is 40 times in 5 minutes. Okay? Now, frequency is cycles per second. So we need to change this to, in 1 minute, there's 60 seconds. So it would be 40 times in 300 seconds. That's the frequency. And we can figure that value out. It calculates to be what? What'd you get, Princess? 0.13 repeating hertz. So we have frequency, we have wavelength, we're looking for velocity. Velocity can be solved by v is equal to f lambda. So 0.13 repeating hertz multiplied by 4.0 meters. How much? 0.53 repeating meters per second. The question tells us 2 significant digits, so velocity is equal to 0.53 meters per second. Okay? All right. Let's look at some theory questions. Okay. A teacher creates a wave in a rope which is fixed at one end to a wall by sending pulses through the rope by simply moving her hand and flicking the rope up and down. Describe what would happen to the wave's amplitude and speed if the teacher puts more energy into the wave without changing the frequency of her hand's vibration. So let's just, the amplitude would increase. What's the reasoning for the speed staying the same? Can you answer that piece, Daniel? Yeah. Right. Excellent reasoning. The simpler reasoning, that's excellent. That's absolutely not wrong. The simpler reasoning is that I didn't change the medium. Okay? But you're absolutely right in your reasoning, Daniel. You were not wrong at all. Okay. Describe what would happen to the wave's frequency and speed if the teacher puts more energy into the wave by increasing how fast her hand vibrates up and down. Okay, but just like Daniel pointed out, the wavelength will decrease. Okay, excellent observation.